Hey everyone. So in this video, I want to show you a better way of running OpenSees analyses rather than just using the analyze command statically. And by that, I mean just passing the number of steps you want OpenSees to analyze and letting OpenSees run for that many steps. You may recall in the last video, I said that this is definitely not my preferred way of going about things. So I'll show you how to run what I like to call an analysis loop. Um, we're going to be taking a look at the cantilever I presented in my pushover video. If you haven't seen that video, it's not that important to know for this one, but just know that we are doing pushovers of a cantilever. I think the actual analysis loop will kind of stand on its own though. But we're going to kind of be using that as an example. I will run the analysis from last time without making any changes, but I'm going to turn off the load control of force and the displacement control of force. There isn't really any particular reason why I'm choosing this analysis over the others. This is the curve that we ended up getting. The analysis did fail before completing, but we were able to see a fairly decent amount of the pushover curve for the model. Let's now do something a little bit weird. Let's try to break this model. I'm going to put a much tighter tolerance for the normal displacement increment. Now this, for our model, is tighter. This isn't that crazy tight of a tolerance in general. I'd still say this is like a fairly normal value to use. So it's not that crazy to do something like to have this tolerance, just so you know. But what's going to end up happening is our model is going to end up breaking pretty convincingly. And by that, I mean when we run it, the analysis now fails much earlier at a load factor of 157, we can see down here. And we can just visually see we're getting a lot less of the curve. So obviously it's failed a lot earlier. And so I want to do this just because when I defined this analysis, I kind of chose the parameters and did a lot of fiddling behind the scenes to make sure that we got a result that was good and made sense. Uh, but for a lot of the models that you will probably be dealing with, you won't have that luxury, or you'll have to do that on your own. So you might end up in a situation where you know realistically you should be getting a lot more of the pushover curve, but you're not able to actually get that in the model. So let's try and troubleshoot a way of pushing past this point of early failure. You might, and let's do so without changing the tolerance. Let's say we can't change that, because obviously if we just change this back to 8, we press run and everything's good. So something that you might think about would be to change the time step. So maybe we're using a load control where the amount between time steps is 1. So when we go from time step to time step, we scale we go the whole step. And you can see that over here. If you look at the right or the most left column, that output is the load step. So we can see we're going cleanly from 1 to 2 to 3, etc. So I think this is like a logical place that most people will probably start with. You think that if we're failing at 1, maybe if we go to a smaller load step, we'll finish the analysis. So let's actually change the value and see what happens. So we tried 1, let's apply half and just try to run their analysis. So with half the load step, we fail. We don't actually even finish 1 load factor. like one step in our analysis. So this seems like a little bit weird to start off with, right? You kind of expected that, okay, one worked, 0.5 doesn't work, so a little annoying. Let's try some other time steps though. Let's try 0.2. Can we get anywhere with 0.2? Nope. All right, let's keep going smaller. 0.1. Let's run that. Huh, 0.1 does work, but it's even worse than 1. So this was our analysis with where we were incrementing the time step by 1 each time. This time we're incrementing by 0.1. So, and just to highlight that, if we look at the output from the recorder, again, we can see we're going up 0.1. So this is even worse. But let's say we were super persistent. We imagine that if we just keep going down in the time steps, eventually we're going to reach something that's reasonable. That's probably a reasonable speculation to have. So let's try going even smaller. We'll go 100 times smaller than the original time step. Now we run the analysis. Hey, we got farther than the past time. And we can see, however, we're doing 5,000 time steps, and we're getting a very, very small amount into the displacement curve. So we can imagine to capture this displacement curve, we need to push the model to at least like 0.3 percent, and we're like almost 100 times smaller than that. So we speculate that a smaller time step is better, but we don't actually, we can see that that's not actually always the case, because as we went from our curve where the time step was 1, we actually had a worse result when we went to 0.1, but a better result when we went to 100 times smaller. And I think this can kind of highlight some of the problems that you might get into if you are just trying to rigidly apply the same settings to every single time step in your analysis. Like we said, we speculate that if we were to try like something like, I don't know, like 100 or 1,000 times smaller, we hopefully would be able to capture more parts of the curve. It's just we also it's ridiculous to use that many time steps in the analysis, because clearly for some of the time steps, the much larger change will work. So instead of running the analysis with this kind of fixed setup, what we can instead do is we can run the analysis with a set of conditional statements. So imagine instead of just having this analysis, and we can replace, this analyze command, we will replace it with a for loop. So we'll say for, and I'll use n as our counter, I guess. Yeah, it's already there. So we'll use this n as a counter. So for n in range, I'll just get rid of that, number of steps, we will analyze once. Okay, so we've really made no changes at this point, and I will comment out this OK above and copy this OK back down. Okay. So we haven't really made any changes. We're still going to run the same amount of analyses, but now we can try to apply some conditional statements to our analysis to see if we can maybe mess around with our time steps and see if that gets us a bit of a better result. So you will recall OK will return a 0 if the analysis is OK, and it will return some other flag if it's not OK. So basically, we know that if OK is 0, our analysis is good. So we're pretty happy using this amount for the load control. And so I am using the load control to mess with the time step instead of something like 0.1 in the actual analyze command. But yeah, so we do want to use this fairly big time step for early on, but let's also try, so let's say that if we get a failure, so if it fails and OK isn't equal to 0, then let's try something. Then say let's try reducing the time step size, then analyzing again. Let's also maybe give a bit of an indication that we have entered the loop. So this will just help us when we run through the analysis. It will be useful for us to know that the program is trying a different time step. So we'll do print trying smaller time step. At load factor. Okay, so when we enter the loop, or excuse me, if we enter this smaller loop, we'll print out the time step that that happens at, and this will just be useful so we can tell when things are going wrong. I also want to, if we fail again, instead of running, so one challenge with this setup right now is if we fail, we will keep running for the same amount of time steps, which isn't really ideal because nothing's changing. So we're just going to be running a whole bunch of failed analyses. So we actually can get around that though by adding a break statement to our loop. So we'll say if OK equals 0 again, we'll print ourselves a little message. We're saying, so we'll tell us that the analysis failed. We'll say load factor. Time step load factor. It's basically the same for a static analysis. Oh, but okay. So we'll print that message and then we'll break the loop. And that way, like I said, we don't end up printing a whole bunch of gunk that we don't, or running the analysis a whole bunch of times that we don't need to. So let's go and try running the analysis again and seeing where that gets us. I will compare with the original curve. So let's just run it and see what happens. Okay, so we can see that the analysis actually fails. And we can, so it fails where we expected it to fail at 256, and then it tries a smaller step. It tries another smaller step at 164, and then it fails again. So if we can see, not that different looking. We'll go in and we'll look at the pushover plot. Okay, so we can see that we get a little bit farther, not very much farther, but we are able to kind of push past that initial failure point and try again with the smaller time step. So let's keep going. Let's add another another trial to our loop now. Oh, actually, before we do that, I forgot to do something. So when we set the load factor down here, we actually should reset it again. So we changed the load factor to 0.1, but really we want to be starting at the initial load factor at every step. So I'm just going to run again and see if that if we change much. Okay, so that does get us a little further than we were before. So here we're at 300,000 kilonewtons. I think this is shear. Could be shear a moment. Anyway, we'll say it's kilonewtons. So yeah, 30 kilonewtons here, and then we get to 35 kilonewtons here. So we can see we're already doing a little bit better with our iterative process. But yeah, let's copy this guy again and see if we can get farther by just trying an even smaller time step. So to reiterate, we try the first time step, which is a full time step. We try a second iteration at 0.1, and then a third at 100 times smaller. And then if none of that works, we end the analysis, we exit our loop, and we cry ourselves to sleep. No, we'll get there. So seeing running again, we're able to get a little bit farther. So this is good, but clearly we still need some work if we are going to be able to capture the full curve. So this helped some, but we weren't able to get all the way just yet. But before we do that, I'm going to be a real stickler here, and let's rename these print statements to something that's a little bit more sensical. These are, excuse me, a little more explicit. So we'll say trying 10 times smaller. And then here we'll put 100 times smaller. And so I just don't like how these messages weren't saying the same thing. Excuse me, we're saying the same thing. So if we look at the outputs, this is it's not helping us very much. We see that it's trying it twice, and then we have to go look up what's going on. We don't really want to do that. But yeah, okay, so let's now, so we could continue this process. We could continually do smaller and smaller time steps. 100 times smaller is pretty small. I would never go smaller than 1,000 times smaller. But something else we could do is we could actually change the number of iterations that we do. So let's say we instead we do the same time step and we do more iterations. So instead of 50 iterations, I don't know, let's put in 200. Typically, you don't really like. I would think 1,000 time step or 1,000 iterations is a lot of iterations. I think somewhere around 50 is like a good amount of iterations. But anyways, so what we're doing here is we are with the smaller time step as kind of our act of desperation. We are trying just to do extra iterations. Although I really shouldn't say this isn't desperate. We could get trying smaller iterations is actually perfectly fine. It would take a lot more to get us feeling a little bit desperate. But okay, getting back on track. We do want to add this command at the end, just to, and actually we should add it. Okay, so I'm going to leave this like this. One comment I'm going to make though is it's a little bit inefficient to set these commands at the end of every analysis, no matter what, because we don't need to, like, say we don't encounter any problems, we don't actually need to change these guys. Okay, you know, I will move this. I don't like how it looks. Okay, so I'm not going to, sorry, being very indecisive. I don't like how this looks, just for like the sake of the tutorial and like showing you how things work. But I probably would, like if I was running this analysis myself, I would probably have these guys up here, and I'd have one in every loop. And so that way we only use the code if we need to. So if we change the load control, then we'll change it back afterwards, and we're not changing it at the end of every analysis. Just a little bit more optimal. But like I said, it's a little bit messier, so I won't do it like that for your sake. Okay, so we have now set up this extra step where we try doing 100 iterations. So we'll just make sure the message reflects that. So trying 200 iterations. That word doesn't sound right. Anyways, sometimes words don't sound right. So we'll try main analysis. We'll just run. So okay, great. So we're able to get even further with this setup. Let's try one last thing. I'll copy paste this above statement once more. And now instead of trying to change the iterations, we'll instead use a different algorithm. So we'll use, instead of the Newton algorithm, we will try the modified Newton algorithm. And so trying modified Newton. Such. And I don't like how this doesn't stay load factor. All right. So now let's try and run our analysis. Oh, and actually before we run our analysis, at the end, let's set this back equal to the Newton algorithm. And let's see what happens. Actually, being indecisive again, I will set the load factor back to 1 in our modified Newton example. Excuse me, the time step back to 1. All right, I think that's good. Yeah, so let's run it. We can see we get a whole bunch of these messages. So clearly it has gone down. We can see that it's doing a whole bunch of smaller time step. But the punchline is we're actually able to get a really good picture of our curve. In fact, we did even better than the original curve. And we have a much tighter tolerance up here. So you can see how powerful this method of running the analysis is. I will make a few comments. Obviously, every single time we kind of dip into one of these loops, we're adding more time to the analysis, right? We're running 5,000 steps. So every single time it's going to check these if statements 5,000 times, set this back, 5,000 times. That will add up. So we do want to be a little bit careful here. We don't really want to go willy-nilly and just have like an insane amount of things that we try. I think you want to be really judicious with the options that you're selecting in here. So just a word of caution, you definitely don't want to go overboard. But like I said, you can see the results, how powerful this sort of thing is. So I'll show you just a few, 2 more quality of life things that we can do to kind of make this process a little bit more efficient. So it will probably be convenient to have all of this be within its own function. So you can imagine you might want to use this code on, say, a different analysis, but it'll be convenient for our purposes to create a function that does a loop for us. So I'll call it define, we'll just say basic analysis loop. This loop, and we'll get to the input arguments in a moment. All right, so we're going to need to pass OK in to the loop, and we're also going to need to return OK from the loop, and we're going to need to know the value of n if we are to print out anything successfully. So we can just grab that. We'll go back to our loop. And oops, I think I got too much there. We want to have the break statement outside of the loop, just because I mean, you can have it in the loop, but it will show up as an error, and then Python, yeah, IDE will get all mad at you. So better to have the break outside the loop, in my opinion. And we're returning okay, so we'll have this like such. So now we have this function. If we wanted to say, if we wanted to include this in our other analyses, it would just be a matter of copy and pasting the function in there, as well as the loop. So this is looking good. As a very last thing, right now we are running the analysis for a fixed number of steps. So we've actually gone in and we've told Opensees, hey, we want to run the analysis for 5,000 amounts of steps. But generally, when you're running an actual analysis, you don't want to run it for a fixed amount of steps. You want to run it for some criteria. Like, for example, let's say we want to run the analysis until displacement reaches 0.5 meters. So we can actually go about doing something like this. If instead of using this for loop, we use a while loop that checks a condition. So I'll get that set up. So we're going to use n as our counter still, and I'll get rid of this now. So instead, we're going to use this while loop, and we're going to check a condition. So I said that the condition that maybe we want to check is the displacement at the top of our structure is 0.05 meters. So we can actually do that using the Opensees output command. So there's a command, what is it, node displacement. This command returns the the displacement of a node that we want. So we'll use the control node and the control node degree of freedom. So this will give us the displacement at the node we want and the degree of freedom we want at the current time step. And we'll just say it's less than, well, that is less than 0.05. So in our case, we want, yeah, that's the criteria that we want. And in fact, now we don't even need to have the number of steps. So I'll just, so yeah, let's create a variable and call it displacement max. So max, and we'll use that. And so we'll pass that to our function. Before we make the changes in main analysis, I have made an error here. Actually, this needs to be within the for loop. So I'm just going to change that, because we only want to run the analysis loop if the initial analysis fails. So yeah, we'll do that. I'm thinking out loud, when we look at this analysis function, we change back these variables, but we do so within the function. And maybe so in terms of reusability, that maybe isn't the best way to go about things, just because now whenever you reset these factors, they're being set to whatever was originally in the analysis. So it's kind of constrained to the analysis, even though it's outside of the analysis, which isn't, I don't really like that so much. So it might be better to take this section and take it outside of the analysis. I'm not going to do that for this case, but I think this is something for you to consider if you want to have like a really reusable function that can be used not just for like this one analysis, but say like a set of different analyses, then maybe that's something to consider. Oh yeah, and so before we go back to main, we also will increment our counter. So we'll add 1 to the counter at the end of every loop. All right. Yeah, that looks great. So, you can see my little debugging console. I did not catch this the first time. So, but anyways, so let's go back now and so we'll need to change because we've now changed the displacement max. I'm going to haphazardly change the number of analysis steps to that variable. It's probably, you know what, let's not do this. Let's just put a value in like, oops, let's put a value in like this. Probably should give it a variable, but we're in the home stretch. So if we run it, we get all these iterations. We can tell the analysis is doing stuff, and we see if it goes to the final amount that we want it to go to. So if we look at our displacement out, we can see all the way at the bottom, the displacement is the correct displacement, and we can see the load step. So we can maybe have a little bit of fun. See if that's asking for trouble. I'll do 7 or 07. So we'll just see how far we can get this to go. Pretty much done at this point. So yeah, so we can see even with our more flex, we can see we can get to 0.7 meters even with, because of this really flexible way we've defined our analysis. So if we were just using single analysis steps, I think it would be really tricky to get this sort of result in a clean way. So that's it for this video. In the future, I'm going to be taking a look at how to do some plotting and also how to do cyclic pushovers. So we'll take the same beam and we'll try and do some cyclic, like reverse cyclic loading on it. So that'll be fun.